Okay, so yes, for student online, student attending Yangting, could you check whether you can see my slides and hear my voice? Student online? Okay, good. So, yes, good afternoon, everyone. So, time for us to start. For us to start the class. So first, let me start the recording. Okay, so today, we are going to learn chapter 5 on electromagnetics. So all the contents on optics has already been finished. So that I think this Saturday we will have quiz 1. So that will cover all the content on optics. You know, chapter 1 to chapter 4, also tutorial 1 to tutorial 4 on optics. So that it's time for you to start review, to do the revision. If you have anything unclear or have any doubts, do remember we have this Friday afternoon consultation. So this week, I think, please try to fully make use of that consultation. If you have any doubts, try to clear that and try to make sure you understand that you are clear about everything before you attend the quiz. Okay. So as I said, quiz 1 to be conducted is how we will conduct quiz 1 is there will be six MCQ multiple choice question, so that you have to solve within half an hour. Okay, half an hour. So only one correct choice for each answer. But maybe there will be 5 or 6 options. You have to choose the right one. Okay. So now today we are going to learn electromagnetics. So that is the second part of this course E1102. So that for electromagnetics, basically we will have 9 chapters to be covered in 5 tutorials. Okay, tutorial 1. So our class today will concern about electric fields. Next week, we are going to talk about one of the most important law in physics and also mathematics, that is Gauss's law. So lecture 3 covers electrical potential and capacitance. So basically chapter 3 and chapter 4. Now, this is where quiz 2 will cover. Okay, the quiz 2 will cover the first 4 chapters on electromagnetics. So that is the first 3 tutorials on electromagnetics. Okay, but if you review the last lecture notes, so that is the first 4 chapters, and then that to be covered in the next 3 weeks, including today's one. Okay, so this is where quiz 2 will be tested too. Okay, so it will test all the contents on electricity. And then the last 5 chapters about magnetic fields and EM wave. So that will be covered in lecture 4 and lecture 5. Okay. So in total, 5 weeks cover this 9 chapters. The last 5 chapters will not be covered in quiz 2. Okay. Quiz 2 only the first 4, but the first 3 tutorials. Okay. Any question here? So no question now. So today we are going to talk about the electric fields. So basically there are 6 subtopics. As long as you understand these 6 subtopics, and then you are fine about this chapter. So first we have to understand what are the properties of electric charge, and then how to distinguish insulator and conductor. Then what are electric force and the electric field, And then how to calculate the electric fields due to multiple point charge or a continuous charge distribution. Okay, so the last topic is how to use the electric field lines to visualize the electric field. Okay, so first the property of electric charge. So there are 4 properties about the electric charge. So first, in the universe, we only have 2 kind of different electric charge, one positive, one negative. Only this two. Okay. And then the second property is the like charge will always repel each other, while the like charge will always repel each other, while the unlike charge will always attract each other. So that says if we have 2 positive charge, the force between them is repulsive. So the force will be repulsive if we have 2 negative charge. But if you have 1 positive and 1 negative charge, and the force between them is attractive, they will attract each other just like the gravitational force between 2 objects. Okay. So the third property is that electric charge is always conserved. So in the university, the total amount of electric charge is conserved. You can never create or destroy an electric charge. Okay, the total charge is conserved. So the last property is that electric charge is quantized. So what does this mean? So which means the charge taken by an object can only be an integer times the smallest quantity, the minimum quantity E. So E is what we call the animating charge, so which is equal to this value, about 1.6 times 10 to the minus 19 coulomb. So any charged object must take an electric charge, which is the integer times this number. For example, you cannot get a charge, an object whose charge is just, for example, 1/3 or 1/2 of this quantity. So you can never get that. It's always an integer times this number. Okay. So this is what we call quantized. So I would say among all this, the third property is the most important one. Okay. So that is the the charge must be conserved. Okay. So our tutorial question 1, concerns about this. So I will come back to this point later. And then material. So we can categorize material into 3 categories according to how the electric charge or electron moves in the material. So the first part is what we call electric conductor, such as aluminum, copper, gold, silver. So this kind of material contains free electrons. So what does free electron mean? So free electron means, for example, this red dot can respond to the nuclei, so that is an atom, so which is fixed in the material. Okay. Then if this material contains so this blue dot, okay, which is moving is the electron. If your electron can move in between atom to atom without any, without any friction, or maybe not without any friction, but is not bounded to any atom, it can transfer from one atom to the other. So like this one. So this kind of material is what we call conductor, because electron can freely transmit it from one atom to the other. In this case, once we apply a voltage across the conductor, we will be able to drive a current across it. Okay. So this is what we call conductor. So in most of the case, we will have the insulator. We have an insulator. So what does insulator mean? So insulator, on the other hand, the electrons are all bounded by the atom. So even you apply an electric field, you will only shift the negative electron a little bit from the atom, but you cannot completely make it free. You cannot transmit one electron from one atom to another. The electrons are all bounded to the atom. If you apply electric field, it is still bounded to the atom. So in this case, if we apply voltage across the conductor, you will not be able to get a current. So this is what we call insulator. So you cannot drive a current across it. That is insulator. Okay. So the third material is semiconductor. So whose property is between conductor and the insulator. So in nature, a pure, for example, semiconductor such as silicon or germanium, it cannot conduct current. But we can make so it behaves like an insulator. But we can easily make this kind of material to conduct current like a conductor by dope it with some impurity. For example, we can remove one atom of this silicon and dope it with phosphorus or boron, and then this kind of impure silicon, or we call P or N doped silicon, can conduct current. So that this is why the semiconductor has a property between insulator and the conductor, because its pure form is insulator. But once we dope it with some impurity, it can conduct current. Okay, this is semiconductor. Okay, so that's yes, this is how we classify the two material. And then the last property, what we have to understand is that if we put two conductor in contact, the electric charge will be redistributed across the two conductor. Okay, because the charge electron can freely move across the conductor. So of course, if two conductor and electric contact, charge from one conductor will be able to transfer to the other. So especially if the two conductors are identical, for example, we have two spheres of the same size or two cylinder with the same size. Once they are in electric contact, and then the total charge will be equally redistributed across the two conductors. For example, if one is neutral, the other is charged, we put the two identical conductors together, and then this total charge will be redistributed equally across the two conductors. Okay, so this property is what we need to use to solve our tutorial question 1. So our tutorial question 1 says, here we have a metal sphere A initially charged as Q, and then two identical other sphere B and C. Okay, so their size are the same, except that they have 0 net charge. So first we use A touch B, then separate the two spheres. So in this case, A and B are both charged. Then we use B touch C, then separate B and C. Finally, C touch A, separate. I want to know how much charge is on each sphere at the end. Okay, at the end. So now, use the property I just mentioned to you. The total charge has to be conserved. When two conductors contact each other, charge will be equally redistributed across them. Okay, so when A touch B and separate, can you tell me how much charge on A and B now? How much charge? Very good, yes. Half on A, half on B, right? So now A and B both have Q. C there. Now okay. Now the second step, so you can say both A and B Q divided by Q. Now I use B touch C. Now B is Q divided by Q, C is uncharged. Then in the second step, how much charge are B and C? Yes, half of Q divided by 2, so which is 1/4 divided by 2. So which means in this case, because B initially uncharged, B is charged to Q divided by 2, C is initially uncharged. So that this total charge Q divided by 2 will be equally redistributed on B and C. Okay, so that we get Q divided by 4, 1/4 on both B and C. Then finally, now in this step, A still half Q, B and C is 1/4 of Q, Q divided by 4. Now if I use A touch C, how many charges on A and C? In the last step.
Average.
Sorry?
The average.
Yeah, very good. So that is what we should do, is do the average. So you remember in this case, A half Q, C half quarter of Q, so the total charge is 3/4. Okay, total charge is 3/4 of Q. This 3/4 of Q has to be equally shared by A and C, so that both of them should take 3/4 of Q divided by 2, which is 3Q divided by 8 after separation. So in the last step, A half 3Q divided by 8, B half Q divided by 4, while C has 3Q divided by 8. Okay, any question? So now good. So now the third subtopic is about electrical force. So for electrical force, in this part, we only have one formula, Coulomb's formula, and 3 points to understand. So first, The magnitude of Coulomb force is given by this formula. Okay, the velocity of the electric force is given by this formula, what we call Coulomb's law. Okay, so F is the force between the two particles. Ke is a constant given by this number. Okay, Q1 and Q2 is the charge taken by each particle, and R is the distance between them. R is the distance between them. So that Fe is equal to Ke times Q1, Q2 divided by R squared. Okay, so this is Coulomb's force. So the 3 points, are related with the magnitude and the direction of the Coulomb's force. So first, from Coulomb's force, we can say that Fe is inversely proportional to R squared. Okay, this is the first property. So the second property is Fe is proportional to the product of Q1 and Q2. Okay, so the more the charge we have, the larger the force we will get. So the first point, the farther the particle from each other, and then the force will be smaller. So the last part is related with the direction. Okay, is related with the direction. Attractive for unlike charge. So if Q1, Q2 have different sign, that will be an attractive force. On the other hand, if Q1, Q2 have the same sign, we will have a repulsive force. Okay, so 3 properties and 1 formula. Okay, any question here? Okay, so this is the Coulomb's formula in the scalar form. We can, because we already know force is a vector, we can also make a Coulomb's force into this vector form. F12 equal to Ke Q1 Q2 divided by R squared. Look, R is the direction from the source charge to the charge experienced force. So for example, F12 means the force charge 1 exerted on charge 2. Okay, the force charge 1 exerted on charge 2, so that R should point from the source charge to the point charge. Okay, so that the Coulomb's formula tells us that F12 equal to F21 because according to Newton's third law, okay, the two forces must have different direction, okay, the same magnitude. Another thing is, okay, so according to the scalar form of Coulomb's formula, okay, so remember the direction vector here give us the direction of the force that is from source charge to the charge experienced force. What we have to understand here is repulsive force here is always positive because Q1 times Q2 now, okay, if it's like charge, Q1 times Q2 is larger than 0. So this is a positive charge, or this is a positive value. If Q1, Q2 is negative, which means this is attractive force, which is a negative force. So in the vector form of Coulomb's formula, repulsive force is always positive, while attractive force is always negative. Okay? Okay? So if no question, so let's first take a look at this MCQ before I continue to do the tutorial. Okay, so here I have 3 positive charge, 2 capital Q on left and right. Then I have a lowercase q placed on the middle, D to the left charge, 2D to the right charge. I want you to find out the magnitude of the electric force on the middle charge, lowercase q. So you can see this question on our learning catalytics, okay, with this session number. I have already delivered this question. So you can log into learning catalytics using our course sites, okay, or directly type within this session number, okay. So I'll give you 3 minutes to submit your answer. Okay. So look, these are some questions related with your quiz 2. Okay, quiz 2 will test a similar question like this one. So do pay attention here and try to solve this one to say whether you can get the right answer. If you can, and then try to let me know or what is unclear. Okay, so thumbs up. So let's look at the solution. Okay, so clearly, can you tell me the middle charge experience how many forces? How many Coulomb forces? So experience 2, right? Because there are 2 charges on its right and the left. So that we have to calculate the different Coulomb force, one by one. So for F1, KEQ 1Q2 divided by the distance d squared, so that we get F1 equal to 5.5 Newton. So could you tell me what's the direction of F1? What's the direction of F1? Yes, very good. It's to the right because it's repulsing both positive charge. It's to the right. And then if we look at the left charge, okay, so F2 is equal to still Ke times Q, the product of their charge divided by R squared. Now R becomes 2D, so we get 1.38 Newton. So can you tell me what's the direction of F2? This is also unrepulsive force. What's the direction of F2? Very good, it's left, okay? Because positive force, this should be from the source charge to the charge here on the left. Then I have a question for you. In this case, should I use F1 plus F2 to get the total force, or F1 minus F2? Very good. If you want to use plus, you need to make sure the 2 force F1 and F2 are along the same direction. But if they are along different directions, you need to use minus. So that my total force is F1 minus F2, which is 3.1. Oh, sorry, 4.13 Newton. So we should choose D. Any questions here? So now let's look at question 2. So question 2 is more or less the same. Okay, more or less the same. So here we have, 2 positive charge, 3Q and 1Q fixed at opposite end of an insulating rod. Okay. So that these are fixed, and then I have a third charged bit which can freely move, across this bit. So that what I want is ask you to find out the position at which the third bit will be the equilibrium. In equilibrium, which means the total force experienced by the charge is there. Okay, total force experienced by the charge is there, and then whether it's a stable or unstable equilibrium if this is a negative charge. Okay, so you can say if this is, for example, a negative charge, okay, the force F1 exerted by 3Q should be attractive now, right? So that should be to the left. Then for the right charge, this is left, and then it should also be an attractive force to the right. So which means this attractive force will also be on different direction. If we want the total force to be there, what we want is the 2 force F1 minus F2 equal to 0, right? Very good. So this is what we should do here. The first force is Fe times 3q source charge. It carries a charge q divided by the distance. I assume this is x squared. Okay, x squared. The other is KEQ. The other second force F1, okay, and F2 is KEQ times capital Q divided by this distance d minus x. Look, I assume this is x, so that this guy should be d minus x squared. Okay. As I said, because they are along different direction, one force along positive x direction, the other force along minus x direction, because they are along different direction. So I should use this guy minus this one. So now we cancel out all the common factors, such as Ke, Q, lowercase q, capital Q, as well as the direction vector I, so that you can simplify this equation. I set this to 0. So that I did this guy equal to this guy. Okay, I did this guy equal to this guy. So that I just get 3 divided by x squared equal to 1 divided by d minus x squared. Solve this equation, you can get my d is about 0.634 times d. Okay, 0.634 times d. You can really get that. So the second question, the second part of this question wants us to comment on whether this is a stable or unstable equilibrium. Okay, so actually this is related with some content in the mechanics, in mechanics. So what is stable equilibrium? So stable equilibrium means my particle here is in the equilibrium point 0 net force. Now I assume there is a perturbation makes the particle shift a little bit from the equilibrium point. And then of course in this case the net force will no longer be 0. Whether this non-zero net force will be push this force back to the equilibrium point or move it further away. If this particle shifts a little bit from its equilibrium point, the net force tries to push it back to the equilibrium point. We call this stable equilibrium. But if this net force tries to shift the particle further away from the equilibrium point, we call this unstable equilibrium. Okay, so now, in order to understand whether this is stable and unstable equilibrium, we need to understand whether the force F1 due to the left charge and F2 due to the right charge, how they change, according to the distance between them. Now I still set, this is x. When x increases, the force between the left and the middle charge will decrease, right? Because x increases, the distance decreases. So that we get this F3q. Again, this is attractive force to the left. It will decrease as a function of x. On the other hand, when x decreases, the charge between the distance between the middle and the right charge will decrease. So according to Coulomb's formula, when r decreases, and the FQ will monotonically increase as a function of x because the distance between the two charges is decreasing, so the force increase. So just as the equilibrium point, the two forces are along different directions, one left, the other right, and at this point they are the same in magnitude, so that we get 0 force. Okay, so you can say on the right, FQ larger than F3Q. Right, so which means FQ is dominant. So the net force should along which direction? If the particle is shifted to the right. If the particle is shifted to the right, the total force should along the right or left direction. Right. Very good, because in this case, FQ is dominant. FQ minus F3Q is a lot, larger than 0, so it's on the right. Okay, so which means if the particle shifts a little bit to the right, the net force will try to push this particle away from the equilibrium point. Okay, clearly this is unstable equilibrium. So you can also assume this particle shifts a little bit to the left. Okay, so to the left now F3Q is larger than FQ. So that the total charge should allow the total force, the net force should allow on the left. So the particle shifted to the left. The force tries to push the particle further to the left, not back to the equilibrium. Okay, this is also unstable equilibrium. So no matter the particle shift to the left, shift to the right is unstable. So that you should comment on this is an unstable equilibrium. Okay? Any question? Any question for student 19? So no. Yes. So okay. So I should put this on the right. FQ larger than F3Q. So net force on the right. So on the left, F3Q larger than FQ. So net force on the left. So on both sides, the net force try to push the particle further away from the equilibrium point. So it's unstable. So now let's look at question 3. So question 3 is related to question 1. Okay, to question 1, but here we have to do some calculation. So here we have two identical metal spheres. The first attract each other with a force 0.058 Newton. So they attract each other with this force, which means Q1, Q2 are like charge or unlike charge. Yes, very good. So one should be negative, one should be positive. Okay. Then the distance between the two spheres is 1.19 meter. The two spheres are then brought into electric contact. When they are separated again, now they repel each other with another force, 0.0196 Newton. I want you to find out the charge originally on each sphere. Okay, the charge originally on each sphere. Okay, so remember why the two spheres will repel each other is because when they are brought into electric contact, the total charge will be equally redistributed across them. Okay, will be equally redistributed across them. So that their charge taken will change from unlike charge to like charge. So that they repel each other. Okay, understand the process? Good. So now, what we want to calculate is this Q1 and Q2. Initially, they attract each other, means Q1 times Q2 is smaller than 0. Okay, now if you apply Coulomb's formula, bear in mind, as I said, attractive force is an active number. So that the question tells us this is the magnitude of the attractive force. But in the Coulomb's formula, do remember you put a minus sign here because Q1 times Q2 is smaller than 0. So that the attractive force should also be an active value. So that if you rearrange this equation, you can get Q1 times Q2 equal to this guy. But we know one equation is not enough for us to solve two parameters. We need another equation. So the other equation is when the two charges are brought into electric contact, they repel each other with another force. Okay, so in this case, the total charge is Q1 and Q2 plus Q2 equally distributed across the two particles, so that it should be Q1 plus Q2 divided by 2. Now, if you apply Coulomb's formula, rearrange it, you can get, okay, because of this square, Q1 plus Q2 can be a plus or minus this value. Okay, so no matter the total charge is positive or negative, once they redistribute across the two particles, okay, the force will be the same. We will get the same repulsive force. Okay, so even Q1 and Q2, so as long as they have the same magnitude, no matter it's negative or positive, okay, they will repel each other with the same force. So that you can say Q1 plus Q2 have, two different possible values. Okay? Now we have two equations, right? We now have two equations. If we assume Q2 equal to this guy minus Q1 and then substitute in the first equation, we can get a quadratic equation for Q1. On the other hand, if we assume Q1 equal to this number minus Q2 and then replace Q1 with Q2 here, we will also be able to get a quadratic equation for Q2. So one quadratic equation should have two solutions, right? And also there is two different possible values for the sum of Q2. So that both Q1 and Q2 should be able to have 4 values. So when you, for example, for Q1, when you replace Q2 by Q1 in equation 1 here, you will be able to get a quadratic equation, okay? Then and this plus and minus sign are due to the total charge has a possible value. So both plus and minus sign will give us 2 possible values for Q1. Okay, 2 possible values for Q1. So that Q1 have 4 possible values, the same for Q2. Okay, the same for Q2. This is what you should write your answer in this way. Okay? Any question? Okay, so if no question, let's talk about the electric fields. So now you wonder how, for example, the electric force, so how, for example, charge 1 can exert a force on charge 2. So why I think electric force is very interesting is because if you compare with the magnetic force, for example, you learned in last chapter, in last semester. So any magnetic force leads the two particles to be contact, the two objects to be contact. So like the pressure, right? The pressure, you make this object on the desk, you need to press it. You need to give it the pressure, you need it to contact. Friction also needs this object, two objects to contact each other. If they are separate, there will be no friction. Okay, so it's like a pressure or friction, we need the two particles to be contact each other, But the electric force doesn't need it. Okay, even these two charges, are separated from each other far apart. Charge 1 can still feel the force experienced by charge 2. So virtually, you can see there is a certain virtual lines that are connected with these two charges, so that they can experience the force of the other particle. So that virtual line is what we call the electric field lines. So what are the electric field lines? Electric field lines are automatically taken by a charge. So if we have a charge in the space, it will automatically fill the space with its own electric field lines. So it's virtual line, we cannot see it, but it really exists in the space. So if there is other charge enter into the electric field lines of the source charge, then it will be trapped by the electric field lines and then experience a certain force. That is the Coulomb force, the electric force. So that the electric force from charge 1 to charge 2 is exerted from the electric field lines. So that is the physical picture of the electric field lines. Now let's look at how to define the electric field line mathematically. Okay, so the electric field, so actually defined as the electric force exerted on per unit charge on a positive test, on a small positive test charge. Okay, so the electric force acting on a very small positive test charge. So mathematically, E is equal to the force Fe of the source charge divided by Q naught of this source charge. Okay, this is how the electric force, electric field are defined mathematically. E just equal to the force F divided by the charge, test charge number Q naught, Okay, so that's the electric field distribution only depends on the, for example, distribution of the source charge. As I said, once the source charge is fixed, its electric field in the space is also fixed. Okay. So that, of course, it's a vector and its unit is Newton per Coulomb or volt per meter. Now, for our course, we require you to understand the electric field distribution of a point charge. So we already know that for a point source, for example, if we have a source charge Q, test charge Q naught, we already know its Coulomb force is given by this formula, right? It's given by this formula. Now, if you apply the definition of the electric field, E is equal to Fe divided by Q naught, and then you get the electric field of this source charge Q is just equal to Keq divided by R squared. Keq divided by R squared. You can say this only depends on the source charge Q, okay? No longer on the test charge Q naught. So that the electric field of the source charge only depends on the distribution of the source charge itself. So there are two properties related with this formula, electric field. So one related with the direction, the other related with the magnitude. So for direction, if Q is positive, so which means it might have a positive charge, the electric field is always along positive radial direction. So if you plot the electric field lines, so it should point from this particle to infinity along the radial direction. But if this is a negative charge, then the electric field should point from infinity back to this source negative charge. Okay, so the electric field line of a point charge always along the radial direction. but whether it's point to infinity or point from infinity back to the particle depending on the priority of the particle. Positive charge always from the particle to infinity. Negative charge from infinity back to the particle. Okay, this is the first property. The second property related with the magnitude. Okay, E is also inversely proportional to R squared. E is inversely proportional to R squared. So that when we plot E as a function of R, we will get, okay, E monotonic decrease when we increase the R. Okay, any question? Good. No question. Let's look at one past examination papers. So here I have, so this was tested last year, last special term, okay? We have an object of mass 4.5 grams with a charge minus 58 microcoulomb. It was attached to a string and placed in a uniform electric field, which was directed, in an opposite direction, okay, which is directed in this way with an angle theta to the horizontal direction, okay? The object is in static equilibrium when the string is aligned horizontally. Okay, when the string aligned horizontally, which means the string will give us a tension force along the horizontal direction, okay, along the horizontal direction. Given that this tension force in the string is 0.05 Newton, I want you to determine this angle theta, as well as the magnitude of the electric field, okay, as well as the magnitude of the electric field, okay? So this is the horizontal direction, this is the vertical direction. So if you take a look at this particle, can you tell me how many forces this particle experiences? How many forces?
3.
Very good. What are the 3?
Tension, gravity, and electric.
Yes, very good. So first, we bear in mind this is an electric charge. This particle experiences 3 forces. The tension force for the screen, which is acting to the left, okay? Gravity perpendicular to the bottom. Remember, the electric field is elective, or the electric field on this direction. The charge is elective, so that Q times E is a force. If charge Q is negative, the force is on the opposite direction of the field. If the charge is positive, the force is on the same direction of the field. Because in this case, we have this charge to be negative. Q times E should along different direction of the electric field, so that we get the electric force point to the top right direction. Any question? Any question here? Okay, so if no question, okay, now we already get, the plot of the 3 forces. In the static equilibrium, we want the total force to be 0 along both horizontal and vertical direction. So along the horizontal direction, okay, along the horizontal direction, so this is F equal to Q times Z. This is the electric force. Along the horizontal direction, I have Fe times cosine theta, so which is acting to the right, equal to the tension force, which is acting to the left. Okay, this is the horizontal direction. So for the vertical direction, I have F times sine theta acting to the top, equal to mg, the gravity, which is acting to the bottom. So that you can say in this question, T is given, mg is given. The only 2 unknown parameters are F and cosine theta. Okay, 2 equations just enough for us to get, 2 undetermined coefficients. If we want to get theta, we use equation 2 divided by equation 1. So F cancel out each other. On the left-hand side of the equation, we only get tangent theta. Right-hand side is mg divided by t, so that we can calculate theta equal to this way. So which is about 41 degree. Now, if you support this substitute this 41 degree back into the equation 1, you will be able to get F. Once F is lower, you will be able to get E. Okay. So when you do this way, you will be able to get the electric field is about 1149.96 Newton per coulomb. Okay, so this unit should not be Newton. Okay, should be Newton per coulomb. Okay. Any question? Any question? So if you know, actually 2 years ago we tested a similar question. So for this guy, so still this particle experience the electric force, tension force, and the gravity. So you take a look whether you can solve this question by your own. Because of the limitation of time, I will not talk about the solution in more detail. Okay, but the solution provided here, you can take a look after the class. And also, I highly suggest you do yourself and then compare your solution with mine to say whether you can get the right results. Okay. So now the first part is about the electric field due to multiple or continuous charge distribution. Okay. So sometimes we are interested in knowing, for example, the electric field at a certain point due to multiple point charge. Then how we should do the calculation. Okay. So as I said, both electric force and the electric field are vector. So that what we can do is we first calculate the electric field or electric force due to each source particle, okay, each source charge, and then we sum it up them vectorly. We sum it up all the force vectorly so that we can get the total electric field. But how to sum up this vectorly? We always have this three step, okay? For multiple point charge, we always have this three step to get the total electric field. How can we do that? First, we use applied Coulomb formula to get electric field or force due to individual particle. Okay, so that's the way provided in my formula sheet. Okay, in my summary slides, F and E, and then the second step very important here. You need to decompose E and F, E or F into its X and Y components. Okay, you need to decompose this F and E into its X, Y, and Z components. So the last step is you just summing up F, so the X, Y, and Z component separately, then you can get the total force. So the decomposition of the vector is very important. Once you get the force F, you have to find out is projecting on X, Y, and Z coordinates, and then summing up individual, components separately. Okay. We bear these three steps in mind. So I have three questions in the following to illustrate this three steps. For the electric field here, this multiple point charge is the most important one because it was tested very often in the final evaluation, as you will see later. So everyone, you should try to pay attention here. How to find the total electric field due to multiple point charge is the most important one of this chapter. Okay. So here I have three charges on the corner of an equidistant triangle, and then the charge value and the polarity are given here. What I want you to do first is calculate the electric field at the position of 2 microcoulomb charge, so which is here due to the other two charges, the electric field. Okay. Then determine the force on this charge and comment on what will happen if this charge is changed from positive 2 microcoulomb to negative microcoulomb. Then I remove all this charge and put, three identical charge of the same magnitude and sign on the three corner. I want you to find out a point within this triangle where the total electric field is there. Okay, there are three parts. Let's see this one by one. So clearly, the charge at this point experiences two different kind of, Coulomb force, right? Or experience the electric field due to charge 1 and charge 2. So for electric field exerted on charge 1, so the E1 should point to the bottom left direction, right? While the electric field of the negative charge should point to the right. Why? As I said, for the positive charge, electric field should point from the charge out to infinity, while for the negative charge, the electric field should point to the negative charge. Okay? The negative charge, electric field should point to the negative charge. This is why the electric field is in this way. So that we first apply Coulomb's formula to get the magnitude of E1 and E2. This is what I said in my step 1, right? Okay? So E1 is equal to this guy. So E2 is also KEQ divided by R. So that we get this guy. So this is the magnitude. Now we need to decompose E1 and E2 into the X and the Y component. So for E1, can you tell me is X and Y components are negative or positive? For example, the E1 is X component is on a negative X direction or positive X direction.
Negative.
Yes, very good, because it's pointing to the bottom left direction. So to the left, which means it's a negative X direction. So that we have E1X equal to minus E1 because this is 60 degree times cosine 60 degree. So equal to this one. So EY1 is pointing to the bottom. So it's also a negative Y direction. Okay, a negative Y direction is equal to this guy. So this is E1Y and EY2, E1X. So how about for E2? The Y component is how much for E2? Y component E2, yes, very good, because it's completely on an X direction. So that E2Y should be 0, while E2X is exactly same as E2, equal to this guy. Okay, so these are the most important parts for for us to do the decomposition. Okay, to get the total field. Once we do the decomposition, the last part is very easy. As I said, the X component and the Y component, we just the summing of individual components. EY equal to EY1 plus E1Y plus E2Y, so that we get this number. While EX equal to E1X plus E2X, we get this guy. These two cancel each other, we get 19. Okay, 19 here. So that if finally you write the electric field in the vector form, it's 19I minus 200 and 18I minus 218 J times 10 to the third Newton per coulomb. The problem solved. So these are the procedures for applying the three-step method to get the total field. Again, first step, apply Coulomb's formula to individual charge to get the magnitude of the field. And then according to the direction of the field to do the decomposition to the X and the Y components. Then summing of Y and the X components separately. Okay, any question? So if no question, part 2 is very easy. Okay, what will happen? What is the total force? Total force equal to Q times V. We already get it, so that's U times Q, you can get the total force. Now, if Q is a magnitude remain unchanged, but we change it from positive to negative charge, what you will do is you will find the force magnitude remain unchanged, but the direction of the force will switch side. Okay, so just comment here. Okay, when the parameter of the charge is reversed, changes from positive to negative minus 2 or micron coulomb. So that's the electric force will point to the opposite direction with the magnitude unchanged. Okay, with the magnitude unchanged. So the last part is now here we have three charges identical. Three charges identical at the coulomb. I want you to find out a point within this equilateral triangle where the total electric field is there. So first, can you give me a guess? Which point do you expect the electric field to be there?
Center.
Yes, very good. It should be exactly at the center. So what do I mean by the center? So at the center, okay, the center should have the same distance to the three charge. And then the angle between them is 120 degrees. Why 120 degrees? Is because we have three charge. One circle is 330 degrees, so divided by 3 is 120 degrees. Okay? So now we just check whether at this point the field is really 0. So what I do here, pay attention here, what I do here is I first apply Coulomb's law to this three charge. Okay? Because the distance to the three charge are all the same. So that I can say this magnitude E1, E2, and E3 are all the same, right? Because the distance are the same. So that E1, E2, E3 are all the same. I assume this is equal to E naught, okay, E naught. So bear in mind this E1, E2, and E3, the distance between them is 120 degrees. which I already said because at the center. So that's the angular distance is also equally distributed, 120. Okay, 120 degree. So that this is 120. Half of it will be 60 degree. So now I take a look whether these three identical charges in this way will give me 0 at the center. So first on the x coordinates. Okay, E3 doesn't have any contribution because it's only acting on y, direction. So that at the x direction, I have E1 times sine 60 degree minus E2 times sine 60 degree, because one is to the top right, one is to the top left. So that because E1 and E2, they are the same in magnitude, so that the x component cancel out each other, giving 0. Now along y direction, both E1 and E2, they are acting on the positive x direction. So that I should have E1 times cosine 60 plus E2 times cosine 60. So E3 exactly along minus y direction, so that I'm minus E3. Cosine 60 is 1/2. Half E naught plus half I naught minus E naught, I get 0. So that I prove exactly at the center, the total force is 0. Okay, any question? Any question here? Okay, so if no question now, I will share with you, 3 other task examination papers for you to strengthen your concept, your understanding about how to get the charge how to get the total electric field due to multiple point charge. Because as I said, this is the most important concept. I hope everyone of you should understand. My 3-step method to get the total electric field or total electric force due to multiple point charge. So here I have 3 negative charge. Okay, they are equal minus 15 on the corner of an equilateral triangle. Okay, and the side length is 25 centimeters. I want you to determine the direction and the magnitude of the negative force on each particle. Because this is an equilateral triangle, all the 3 charges are the same, so that you can quickly see, the total force of the 3 charges should be the same, right? So once we get the total force of one charge, we can also get the total force of other 3 charges without any further calculation. Okay? So that first, due to the symmetry, let's first consider the force experienced by A. Okay? Okay? So that the A experienced the force exerted by B and C, right? Because they are identical, and the force between A and B and the force between A and C should be the same, right? So let's assume this force is F. Okay? And the 2F, they will form an angle 60 degree because the opposite angle of a equilateral triangle is 60 degree. Half of it is 30 degree. So which means force 1 here is point to a direction which is 30 degree with respect to the vertical. So the same for F2 exerted by charge C. So you can see the x coordinate, one top left, one top right, they cancel out each other. So their y component is F times cosine 30 degree. Twice of it is 2F times cosine 30 degree. Okay? So which means clearly for the particle A, the net force should be 2F times cosine 30 degree. So that is exactly along the y direction. So for B and C, the total force remains unchanged. It's still 2F times cosine 30 degree. But now it does not, just along x or y coordinate. It is along a direction that forms an angle 30 degree with respect to the horizontal due to the symmetry. Okay, due to the symmetry. So this is what you should comment. So first, what you should do is apply Coulomb's formula to get what is the force F, due to particle A or B or B or C. So KEQ divided by R squared, I get this one. Then I get the total force 2F times cosine 30 degrees. Then I can get the total force on each particle. Now I should comment. For particle A, the total force, this guy is directly on the exactly vertical direction. But the force for particle B and C are different, okay? Or the magnitude are the same, but the direction are different. For particle B, the total force is actually to the bottom left direction with an angle 30 degrees with respect to the horizontal. So for particle C, the total force direction is on the bottom right direction with an angle 30 degrees to the horizontal. Okay, so this is what you should comment here. Any question? Any question? Hello? Any question here? For this one? So if this, let's take a look at a more difficult one. Oh, this was tested about 2 years ago. So 3 years ago, sorry. So we have 4-point charge at the corner of a square whose side length is A, as shown in this figure. I want you to determine the total electric force in the vector form acting on the charge Q. So this guy acting on the charge Q due to the other three charge. Okay, so you can say all the charge are identical. You know, they are like charge, or not identical. They are like charge. This is Q. These 2 parts are 2Q. These are 3Q. So they have the same polarity. So that's the force between them are all repulsive, right? Are all repulsive. So if I want to find the net charge on Q, I need to find out the force experienced by this, you know, 3 charges separately. So you can say because of their polarity, repulsive force, so that the force experienced by this charge should be acting on the horizontal direction, which is on the minus x direction, right? And then the charge experienced by this bottom left charge, okay, should be along the vertical direction. Okay, this is along positive y direction. So the charge force due to this bottom right direction, okay, should act on this way, 45 degrees with respect to the horizontal. So we'll first get the direction. And then we apply Coulomb's formula. Again, as I said, okay, the first part is we should apply Coulomb's formula to get the force due to individual charge. Okay, so that for the F2Q horizontal and F2Q vertical, because you know the charge are the same, distance are the same, so that is both KE times Q 2Q divided by A squared. Okay, so this is what we get to F2Q horizontal and F2Q vertical. So for F3Q inclined, okay, inclined here, so that the distance between them is now square root 2 times A, right? Because of this is right angle, this is square root 2 times A. So that when I apply Coulomb's formula is KEQ times 3Q divided by this square root 2 squared, so which is 2A squared. So now I get the magnitude for 3 forces. Any question here? Any question here? Now I get the total force. The second step is the most important one. I need to do the decomposition. So as I said, x coordinate is I, y coordinate is j. This is a unit vector. So that for F2Q horizontal, it's along minus I direction, right? Minus I direction. F2Q vertical is along positive j direction. So I just add the corresponding direction vector into F2Q horizontal and F2Q vertical. So how about the F3Q inclined? The x and the y component are negative or positive. For F3Q, so first the x component is positive or negative? Negative. Yes, very good, because it's to the right. So that is x component is actually the magnitude times cosine 45 degrees, then times minus I. So y component clearly is positive, okay? Y component is positive, so that we use this guy times sine 45 degree, and then times the unit vector of positive y direction, which is j, so that I can write F3Q in the vector form. Okay? Then what I do is summing up the x and y component separately. Okay? X plus x, I get this guy. Y plus y, I get this guy. Then I do a little bit of calculation. I can write f in its vector form in this way. Okay? Any question? So if no question, so the last question I would like you to do, so this is actually a test about 4 years ago. I would like to use this question like MCQ. So here I have 5-point charge are uniformly distributed on a fixed circle of radius r. I want you to determine the net electric field at the corner. So A, B, C, D, E, and F. This question can be solved purely with symmetry. You don't have to do any calculation. Now I will give you 3 minutes to think about, the answer. To think about the answer, maybe you can also discuss within the group. Okay, I give you 3 minutes, and then each group give me an answer. Okay, each group give me an answer. Okay, this one I give you 3 minutes. I give you 3 minutes. Okay, the students are nice, so because you cannot, form a group, so that you just try yourself. Once you're done, you can type your answer on just the chat room. Okay, for student and team. Now, okay. Try to solve this one. As I said, you can solve this question purely with symmetry. Purely with symmetry. Is there any idea? Any idea from each team? Okay, so maybe due to the limitation of time, because we have another sub, I will directly show the answer. Okay, we should choose D. Why D? This is because, okay, first you look at due to the symmetry. Okay, all the configuration are mirror symmetry with respect to each other. Okay, so that you can say F2Q and Q2 and Q5, their X component of the electric force will always cancel out each other, right? So for example, what we say is, for example, for Q, the top one Q1 is exactly on Y direction without any X components. Okay, this is for Q1. And then if we look at Q2 and Q5, okay, Q2 and Q5, they are mirror symmetric. E2 and E5 are the same. They are mirror symmetric with respect to each other, right? So that the X component should cancel out each other. So which means the plus E2 plus E5, we should get 0 X components, right? So if you, the same apply to E3 and E4. Okay, E3 and E4. E3 and E4, they form an angle 30 degrees with respect to the horizontal. Oh, sorry, with respect to the vertical. And the E2 and E5, they form a degree 72 degrees with respect to the vertical. Okay, with respect to the vertical. So that E3 and E4, you can say due to the mirror symmetry, their X component also cancel out each other, right? So which means if E1 does not have any X component, E2 X component cancel out E5 X component, E3 and E4 their X component cancel out each other. They shouldn't get any X component, in the final answer. Okay, in the final answer. And then you can say whether along Y coordinate, it should along which direction. You can say E1 is actually this 2KEQ divided by R squared, right? This is E2. This is my E1. This is my E1. So clearly E2, E3, E5, and E4, they are all the same. They are all the same, right? But you can say because their angle is different, clearly for another Y coordinate, the E3 and E4, their Y component is larger than E2 and E5, right? Right? E3 and E4, their Y coordinate is larger than E2 and E5. So that they should actually try to decrease E1, so that we should get some magnitude that is smaller than this 2K times Q, but it is still negative. So only D. Sorry. Sorry. Oh yeah. Sorry. This should be J. Yes. Thank you. This should be J direction. This is a typo. Okay. Let me see whether I can change it here. Oh, sorry. Yes, this should be J, not I. Yes, that's right. This should be J. This should be J, not I. Yes. So that when you do the calculation, so what you can do is in this way. So you assume EY, for example, equal to 2KEQ divided by R squared. Okay, and then E2, E3, and E5 are all the same. So finally, when you do the calculation, you just assume for example, this should be J. So that EY is on a minus J direction, while E2 and E5, they are on a minus J direction, but their projection is cosine 72 degrees. So the same for E3 and E4, they are along positive Y direction, so positive J, but their projection is cosine 36 degrees. So once you plus them together, you will get a minus JKEQ divided by R squared. Okay, minus JKEQ divided by R squared. So these are still the same. As you can see, first apply Coulomb's formula, and then decomposition. Finally, plus all the X and Y component together to get the total field. Okay, any question? Any question here?
How do you find the degree, the angle?
Oh yes, this is a very good question. So you can say these are 5 particles, right? 5 particles identical, equally distributed on the circle. So which means the angle between each of them, or the angle between each laboring force should be 330 degrees divided by 5. So which means the angle between each laboring line is 72, because 330 degrees divided by 5 is equal to 72. So this is 72, this is 72. E3 and E4, the angle between them is also 72. So 1/2 of it is 36. Okay? Clear? Clear? Good. So which now we will talk about. So here I have some other question about this multiple charge, question. So as I said, it tested quite often in the final examinations. But the last one, I don't have time to go through it. So you try to solve yourself and compare with my answer, okay? So now I will quickly jump to the last chapter, or last part I would like to talk about. So which is the charge due to continuous charge distribution. So first, how important is this value? Because this one is very difficult, okay? You have to do integration. So when you still upon this part is very difficult. But what I tell you is, in the final examination, we have never tested continuous charge distribution. In the final examination, never. But there is a but. In the quiz, we have. In quiz, we have. Quiz, we have. Not many, but maybe, for example, like so in my memory, for example, there are about 10 questions out of 600. Normally, we have 600 questions in the ARS. There are about 5 to 10 questions similar to this one. So which means about 1%. 1% of the question is about integration. So so you know how the quiz will be conducted, right? So each of you will be tested with a different question. When you sit in that computer looking at the OAS, you will be randomly given 6 questions out of 600 questions in the database. Okay? So I mean 1%, maybe you will be get a question that is like the integration, so which will be difficult. But what I would say is this is still required. Although the chance for this kind of question to be tested in the final examination is extremely low, but for quiz, you may get a question like this one. So you still require to understand that. Okay? So first, let me tell you how we should do the continuous charge. So for continuous charge, we just divided this. So we have the charge continuously decrease across a certain object. So it's no longer multiple point charge. So if you want to apply the Coulomb's formula or Coulomb's law, you need to separate or you need to divide this object into very small part. So for each small part, you apply Coulomb's formula Ke dq divided by r squared, and then integrate it over the whole surface or the whole volume to get the final answer. I think there are several examples in the lecture notes, in the last video. Now we also have one property, one tutorial, to illustrate this problem. So first, I would like to use a summary select, force select method to get the total charge, the total field, the total electric field due to continuous charge distribution. So first, you always start with this Coulomb's law. dE due to infinitely small part of this continuous charge. dE always equal Ke dq divided by r squared. dE, okay? Once you get dE, you have to decompose. You have to first you have to write dq. This is the first important stuff. You have to write dq as a function of the coordinate. So find out an expression for my charge dq. So here I have another slide to show you how to do that. But the part 2 is the most important one. So this is one additional step as compared with this multiple point charge. So for multiple point charge, once you get each E and then we decompose it into X, Y, and Z component, summing up them together. But for continuous charge, you first write down dE. Before you decompose it into X, Y, and Z component and do the integration, you need to find out an expression for dq. Once you find an expression to dq, write dq as a function of the coordinate. And then you decompose X, Y, and Z into its, dE into its X, Y, and Z component. And then you can get dEx, dEy, and dZ, according to the direction of dE. And then finally, you integrate dEx, dEy, and dZ to get the total Ex, Ey, and Ez separately. So these are the 4 steps. So as I said, we have additional steps, step 2, to write dq as a function of the coordinate. How we should do that is we have 3 different cases. If we have volume charge distribution, so the first step is always found out the charge density. if we have volume charge, the charge uniformly distributed across a volume. The charge density is the total charge divided by the volume V. If we have a charge distributed on a surface, so we have this charge Q divided by A. If we have charge uniformly distributed on a line, we have lambda as Q divided by the ln L, and the ln L. So once you know the charge density, so that for volume charge, the dq just equal to rho times dx, dy, and dz. If it's surface charge, dq equal to sigma surface charge density times dx and dy. So for line charge, you have dq equal to lambda times dx. So fortunately, for up to now, for all the question I know equation is normally along this line charge. So the charge is uniformly distributed across a line. So you can say orthogonal, and also the question I know in question 2 is always along the line charge distribution. So which means you only need to do the integration along one direction dx. But if it's a surface charge distribution, so as you can see from the lecture notes, you have to integrate it, to do double integration, both integrate along dx and dy. So for volume charge, you need to integrate both dx, dy, and dA. So far we have a lot of constant cases. But what I mean is, for the quiz, you just require to understand that the last part is okay. The last part is okay. So now I will use this example to end the class. Now I have a charge uniformly distributed across this finite rod. Uniformly distributed at the finite rod. At the bisector, I want you to show that the x component is 0, while the y component is given by this equation. Then I want you to show that when this guy changes from finite to infinite, and then the total force, the total field here will be given by this equation 2ke lambda divided by y. So here I also give you some important equation for you to use. Okay, so in your final examination or in the quiz, you use the formula will be given to you. Okay, you don't have to remember any kind of integration yourself. Useful integration will be provided, but you need to understand how to do this, step by step. So as I said, all point is first write dE as a function of x and y. So according to Coulomb's law, dE equal to ke dq times r squared. So again, as I said, this is line charge distribution. dq should equal to my lambda times dx, right? Remember this? Lambda times dx. So once you write dq as a lambda times dx, you also need to change r as a function of x. Okay, so r is actually equal to y squared plus x squared. Okay, now I write dE purely as a function of x and y. So you can say by symmetry, we can say the integration of dEx is 0. Why? Because this is a bisector. For any points on the rod, we can find a mirror symmetric point. We can find a mirror symmetric point also on the rod. So that for the mirror symmetric points, their y component, plus together, while x component can cancel out each other. So that by symmetry, we can find out these two Ex due to the mirror symmetry point cancel out each other, so that when we do the integration, each mirror symmetry point can cancel out the mirror symmetry point's x component. We can get the total Ex equal to 0. Okay, get the total x equal to 0. This is because of the symmetry. So for y component, we cannot do. We can no longer do it by the symmetry. We need to do the integration. So that we need to find what is dEy. So you can say for dEy is actually this dE times cosine theta. So cosine, because we need to integrate across x, so we need to write cosine theta as a function of x and y. As a function of x and y. Clearly, cosine theta is equal to y divided by this r. So r is square root x squared plus y squared. Okay, x squared plus y squared. So that I get my cosine theta equal to y divided by square root x squared plus y squared. Now I can write dEy as a function of x and y, right? So as I said, finally, the total Ey is equal to the integration of dEy from minus the total length is L, so that the starting point is minus L divided by 2. Ending point is positive L divided by 2. So I integrate dy from x equal to minus L divided by 2 to positive L divided by 2. Then you can get this equation, this integration, this kind of integration, exactly the same as the integration I provided in the hint. So that you just substitute what I provided in the hint. You can get exactly the same answer as the question required. So for the last part, I want you to get the field when the total length of the rod goes to infinity. So you can say when the total length of the rod goes to infinity, theta naught will become how much? So for example, if the left end go to infinity, right end go to infinity, theta naught become how much? 90 degree, right? When this go to further and further, this will approach 90 degree. Once it go to infinity, it become 90 degree. So that you just set this guy, theta naught, in the equation we already calculate into 90 degree. You can get, okay, Ey is 2 ke lambda divided by y. Okay, so that this is also exactly the same as what this question wants. Okay, so yes, I think this question is difficult, okay, but it's not so important. As I said, that is still relating to this. Try to take a look at the math here and try to digest it. If you have any questions, just email me or try to find me for consultation. So that this is the end of the class. If you have any questions, so please feel free to ask. Otherwise, the class can be dismissed. Okay. So any question? For student and team? Any question for student and team? So how about student here? Any question? So I think for this question, you should still try to put your full energy on optics part, right? Okay, because we have quiz on Saturday. So that the first do a review of the first 4 chapter on optics. If you have any questions, just try to look for your consultation. I think the most important one is still the tutorial, plus the summary lecture. Because in the summary lecture, the Korean professor already give you, so he also put some template quiz question in the summary lecture. So you can pick up some questions quite similar to the quiz. Okay? So just similar to that. So also the MCQ I put in my tutorial, so that is also directly actually taken from the quiz. So that you can also take a look. Okay? Yes, any question? Yes. Yes.
Sample. This is personal by anti-Christ symbol.
Primary enters a classification on the left, and suppose that is can be located in the left level of the paper. For all 5 ways, experience total internal reflection from the surface. Okay, so if you want to get total internal reflection at this interface, I need to increase the angle. I need to increase the incidence, right? I need to increase the incidence at this surface. Right. I want to increase the creating angle first. I need to make the incident angle approach or even larger than the creating angle in order to get the total internal reflection. Right. Yes. So this is the configuration line. What I want is when light original incident here, right? Original incident here, there have some refraction. What I want is I want this angle, increase this angle so that light can experience total internal reflection at this interface. So if I want to increase this angle, of course, I need to make it more slant in this way. So we rotate it. This is counterclockwise, right?
So if I want a larger, I want an internal reflection, my angle must be large enough.
Yeah,
so I
yeah,
need
yeah.
to see the angle.
Yes. You want this angle to be large enough so that in order to get the total internal reflection. So that you rotate it counterclockwise, okay? So that you can make this angle larger.
But if I start clockwise, then the angle
Will be smaller, and then you will also, in this case, you will always get the reflection. It's not the total internal reflection.
But total internal reflection is here.
Yeah, it says only here, on this surface. It's on this surface. The total internal reflection on this surface.
Okay, that's right. For bright and dark fringes, right? Like, do they tell me which one is the dark, like fringes or I have to know?
So sorry?
Like, how do I know which one is the dark or the bright fringes? Based on the face, is it?
Oh yes, dark fringe always can respond to my delta L, as I say, equal to this is dark fringe, right? Delta L equal to this is the dark fringe. For bright fringe, it should be delta L equal to m times lambda. So how should you know? Is the question will tell you whether to find out the bright and dark fringe. But if it's dark fringe, you put the delta L in this way. Bright fringe, put the delta L in this way.
Just apply the formula.
Sorry?
Just apply the formula.
Yeah, just apply the formula. That's right. Just apply the formula. Let me see. One microscope slide is placed on the top of a non-wire. Okay, so this is actually exactly as a tutorial. So what we are looking at is actually this kind of an air edge. We are looking at this kind of air edge, so which means air has a reflecting index equal to 1. This is reflecting index larger than 1. So that the delta L for this CT interaction is actually equal to 2 NT plus half lambda. So you can see my summary slides, right? For this configuration, delta L equal to 2 NT plus half lambda. So at this edge, T equal to 0.
T equals to 0 at the edge.
T equal to at this, he said the left edge, so I draw it the wrong way. So actually, the configuration is looking like this. So this is actually here, and this is the contact. So that this is the glass, this is the middle part. So at the left edge T equal to 0, so my delta L equal to lambda divided by 2. Lambda divided by 2 equal to 0 plus lambda. But times 1 times lambda. So this is dark fringe.
Okay.
Because this is a half integer, not an integer. So it's dark fringe.
Also, but they got say what? They only say.
They only say what?
So how do you know it's half?
Because T equal to 0.
At here?
Yeah, at here.
Also, it's always 0 at here, the T.
Yeah, of course, at the left edge here is always 0.
Oh, here. Here
is a radius. Here, then the question will tell you what is this T. But the question does not tell you here, so it cannot. So, which means we does not know what happens here.
Also, if they say left edge, just means here is 0.
No, but it says monocorrector lights. What is the left edge of the slides? With the left edge contact each other, right? So which means this is left edge, this is right. So you just try to understand this question. The question said, okay, I have an average for in this way. Left edge can contact each other. The right edge was separated by a hair.
Oh, that's what it means. Oh.
Okay, so that this one is t equal to 0. This is the diameter of the hair.
Oh, then just apply the formula, then
Yeah.
you see which one is the output.
Yeah. And then you get delta L to say whether it's an integer or a half integer. You can see whether this is a bright or dark fringe.
Oh,
Okay.
then right, for just now the tutorial, right, for this question, right, why you need to add and divide by 2 after the
Because the total charge must be conserved, right?
So I must
The
add
total
these
charge,
two
yeah, of course.
together then.
Yeah, because it's the total charge redistributed. It's not Q1 redistributed or Q2 redistributed. It's the total charge
Yeah, I
redistributed.
have to divide by 2 because
Yeah.
of the charge.
Yeah, because you have 2 particles. If you have 3 particles, and then it's a total charge Q1, Q2, Q3 plus together divided by 3.
Oh.
If I have 2 particles, then Q1 plus Q2 divided by 2. So
Then if
always
they
this
never
way.
contact each other, then I just consider one.
Yeah. If we contact each other and then the charge cannot be redistributed, then how many charges is each particle used for calculation. But once they are contact and then separate, the charge must be redistributed in this way.
Oh, okay.
Okay, no problem.
For the charge today, right? What about question? Is it negative? I didn't get it.
Because it's F3Q is acting on the left x-axis. It's what you can say it's the x projection point to the left.
So if it's here, then it will be positive.
Also, yeah, if it's on this direction, it's positive. Yes.
Okay, another question, right, is about the tutorial one. So the last part for question 2, the incident and emerging rays. I still look at that.
The incident and the emerging. So first you have to understand what this question asks for. It asks for the angle between the final reflected angle and the incident angle. This is what we call the emerging ray and the incident ray. So it's asked for the angle between this guy and this guy. So the angle between, for example, this one and this one, so which is this angle gamma, right?
Oh, it's the
So it's asked for gamma. So you can say gamma is actually equal to gamma plus this guy is 180 degree. Total internal angle is also 180 degree. So gamma is equal to this angle plus this angle.
yeah.
So that you need to find out this angle and this angle. So why this is theta 1 divided by theta 2 minus theta 2? This is because you can say this angle, dashed line and the blue line, this angle is theta 1, right? Blue line and the dashed line, yeah, because they cross. So this is theta 1, this is also theta 1. Okay? Theta 1 plus minus theta 2 will give us the alpha 1, okay? This guy, this angle. So you look at the right, because the dashed line and the blue line cross, theta 4 is also this angle. Theta 4 minus theta 2 is the right angle here. So this is theta 4 minus theta 1. So as I already said, gamma equal to left angle plus right angle. So that I get theta 1 minus theta 2 plus theta 4 minus
So
theta 3.
we get these two then. Oh, okay.
Okay,
I think I get it.
are you sure?
Yeah.
Okay, good. So if you have anything, let me know.
For Friday, is it face-to-face consultation?
So it's up to you. If you want to online, you send my email. I can send you my message email so that we can talk online.
Okay.
But if you want face to face, just come to my office.
Thank you.
Okay, no problem.
Question for single state. So for single state, right? The reason why you can't like find bright fringes is because like the rays, their phase are like different when they hit the point.
Yes.
Okay, but how come I can't say the same for double slit?
You cannot say the same for what?
For double slit.
So what does it mean?
Like,
single slit does not have any phase problem.
Like for example, single slit, like we can't find the bright fringes because the phase is like
You can't find the bright fringe.
for single slit.
For single slit, you have a bright fringe. But so this is a bright fringe.
Yeah.
This is bright fringe. But the case is the formula for bright fringe is very, very difficult.
Okay.
You have to use, for example, the formula I give in my, for example, extended slides. So that is not required. So it does not mean we cannot find it. We can find it, but it's not required by the code. By our course, it's too complex.
Okay.
So for that one, it's too complex. So that we do not require you, but you have bright fringe.
Okay.
Single slit have bright fringe, but that bright fringe condition does not require by our course.
Okay. So, but the reason why like bright fringe is complicated to find is because like the phase of the waves, right? Is like,
Yeah. The phase of the wave is no longer distributed. For example, like the double slit. Okay, this is that equal to delta. How to say? That is, I think that like this is L optical path is approximately m. For example, this y divided by let me see, the d times sine theta. Okay, delta L is d times sine theta. So d times sine theta is y L divided y d times y divided by L. So it's delta L. No one calculate in this way. For single slit, no one calculate in this way. But for double slit, we come from a very simple formula for its optical path, so that we can know both bright and dark fringe or any phase, at each point. But for single slit, we can't.
okay.
For single slit, we can't. Single slit, we just know for this one, or is equal to, for example, lambda 0. So, for example, it's pi, or pi minus pi, 3 pi, minus 3 pi and 3 pi. But all the phase in the middle is not that linearly uniformly distributed. But for double slit, the phase difference is uniformly distributed.
Oh, well, why is that so? Is it because like double slit, you just take one wavelet from each slit?
Yes, we just take one wave from each slit, but for single slit, we have many waves together, so it's non-uniformly distributed.
Okay. Yeah, okay, that's
okay.
Yeah.
So for single slit, for double slit, actually, we only take one to work, The condition is, these two, the weights of the two slits must be much smaller than their distance. So if it's, very close, for example, if this gap, the distance is very close to their distance, and then you should, treat it as two single slits, and the phase will also become non-uniformly distributed.
Okay.
But if for example, the thickness of each slit is much smaller than distance, so that we can just treat this as a single ray, so that the phase becomes uniformly distributed.
Okay.
But because of a single slit, we only have one slit, you cannot treat it as a slit. You need to decompose it into very a lot of gap. So this is what I explained to you, not required, for the final examination. But when you treat it this way, put it in very small single slit, and then you will find out actually the phase will become non-uniformly distributed. So which means if we have two double slits, they are very thick. Their thickness is comparable with their distance. You also have to decompose it into very small slit in this way. In this case, you will find actually the phase distribution here is even more complex than the single slit. It's even more complex than a single slit. But under the condition, the weight here is much smaller than D, and then all the phases will become uniform. Okay.
So like if it becomes like two single slit if the distance between the two stays like.
Yes.
Around
It's very close.
So it's around very lambda. Okay.
Yes.
Okay.
That's right. Okay.
Yeah, that's all.
Okay.
But Prof, if for single slit, if we have to find the position for
Dark
bright fringe, we can estimate using the.
You estimate. If you estimate is you can, for example, use a y2 plus y1 divided by 2. You can estimate. But as I said, this is estimate, not exact, not exact location. So normally we won't ask you to do that because that is an incorrect formula. So y1 divided by y2 to find the bright fringe. But if there is some stupid question ask you to do that, there is no way. You can only use y1 plus y2 divided by 2 to find out that. So the middle point assume is bright fringe. Although what I will say, this approximation is wrong. So this is just an approximation, as I say. If you want to know, you need to go to see my you have to go to see my my slides on tutorial 4. So I give you a formula, and then you use that formula to plot. Right? This can give you, for example, for any theta, you will be able to get its intensity. For this formula, at any given theta, you will be able to get its intensity. So this formula can give you, for example, the intensity distribution at any theta. So you will find it's extremely non-uniformly distributed. Definitely not at the middle of y1 divided by y2. Okay.
Okay.
Okay. No problem.
Yep. That's it. Thank you, Prof. Thank you.
No problem. Okay.
Thank you.
So any other? Okay, that's all.
Yeah, that's all.
Okay, good.
Thank you.
So if you have further questions, email me or come to find me Friday afternoon. Okay.
Thank you, Prof.
Okay. Yeah, you're welcome. Okay, so Daniel and Kaya, do you have any question? Hello?
I think there are many also. Like after the
Hello? Student 19? Daniel? Daniel?
Prof, I think they are not there anymore. Because the team sometimes will like show that they are there even though we are recording.
Oh, okay. So maybe I need the session. Okay, thank you.
Thank you, Prof. Thank you.
Okay, good. Bye-bye.
On the